Think about how amazing your brain is just listening to me talk right now.
Yeah, it's pretty incredible.
You're not just hearing separate words, are you? You're getting the context, the flow. Each word kind of builds on the last.
Right. You hold on to the meaning effortlessly.
Exactly. And that kind of um, persistent understanding, that was a real hurdle for AI for a long, long time.
That's a great starting point.
Yeah.
Yeah, traditional neural networks, they treated every bit of info like it was brand new, totally isolated.
No memory, basically.
None. They just couldn't keep that context.
Right. But then came recurrent neural networks, RNNs.
Mm.
Imagine a network, but with this clever little, like, loop. It lets information stick around,
Yeah.
carry over from one step to the next.
It's like giving the network a basic short-term memory.
Yeah, exactly.
And to really get how it works, sometimes it helps to picture unrolling that loop.
Okay.
So instead of a circle, you see it as a chain, like copies of the network all linked up.
Each one passing information along the line.
Precisely. And that structure, it makes them just perfect for sequential data, stuff where the order really matters.
Like words and sentences, like we were saying, or frames in a video.
Exactly. Text, video, audio, anything with a sequence.
And the impact has been, well, huge, right? Speech recognition is way better now.
Oh, definitely. Think about your phone actually understanding you most of the time.
Or those language models generating text that sounds, surprisingly human.
Translation, too. Huge leaps forward. It wasn't just small improvements. RNNs really enabled a big jump. Made voice commands actually work reliably for lots of people.
Yeah, it felt like a real shift. If you're curious about just how effective they became, there's that great blog post by Andres Karpathy.
Ah, yes. The unreasonable effectiveness of recurrent neural networks. A classic read. Definitely check it out if you want to see some cool examples.
But okay, digging deeper. The specific type of RNN that's really behind a lot of these breakthroughs, the real powerhouse, that's the long short-term memory network, right? LSTM.
That's the one. And LSTMs, well, that's what we're really going to dive deep into today. Figure out how they actually work under the hood.
Okay, cool. So why were LSTMs such a big deal? What problem were they solving that the basic RNNs couldn't handle?
It boils down to something called long-term dependencies.
Long-term dependencies.
It's basically the challenge of connecting pieces of information when they're far apart in the sequence. Sometimes it's easy, right? The context you need is right there.
You say the clouds are in the...
Yeah, your brain predicts that almost instantly based on the immediately preceding words. Very recent context is enough.
Simple enough.
But contrast that with, say, I grew up in France. I spent my summers exploring Paris. Blah, blah, blah. I speak fluent.
French. Okay, yeah.
To predict French, the network needs to remember France from way back in the beginning. That's a long-term dependency.
And the standard RNNs, they just couldn't hold on to information for that long.
They really struggled. In theory, maybe they could. But in practice, as that gap between the relevant info gets wider, their ability to make that connection just fades away. They forget.
So theoretically possible, practically very difficult.
Exactly. There was some foundational work back in the 90s that really dug into why basic RNNs had such a hard time learning these long-range connections. Fundamental limitations.
And LSTMs were the answer, designed specifically for this.
Precisely. They were engineered from the ground up to overcome this exact problem. Remembering information for long periods. That's like their default setting. It's what they do naturally rather than something they struggle to learn.
Okay. So there's still RNNs. They still have that chain structure, repeating modules.
Same basic chain-like architecture.
But the module itself, the repeating bit, is more complex than in a standard RNN.
That's right. A standard RNN's repeating module is often just like a single TON layer. Pretty straightforward math.
Okay.
But an LSTM module, it's got 4 layers inside, 4 neural network layers, all interacting in this very specific, orchestrated way.
4 layers working together. Definitely sounds more involved. I remember seeing diagrams with lines and circles and boxes.
Ah, the standard LSTM diagrams. Yeah, let's quickly decode those. The lines, usually with arrows, show how vectors, entire bundles of data are carried between operations.
Okay, like data pathways.
Exactly. Then you have operations. Pink circles usually mean pointwise operations. Simple math done element by element, like adding 2 vectors or multiplying them.
Got it.
Yellow boxes. Those are the learned neural network layers we just mentioned, the brains of the operation, really.
The 4 layers you talked about.
Right. And you'll see lines merging. That's concatenation, just sticking 2 lists of information together end to end. And lines forking. That just means the information is copied and sent to multiple places.
Okay, that visual language makes more sense now. Lines for data, circles for simple math, boxes for network layers, merging, forking. Got it. So what's the absolute core idea behind LSTMs? What gives them this memory power?
The absolute key is the cell state.
Cell state.
Yeah, picture a kind of conveyor belt running horizontally straight through the entire chain of LSTM modules. It's like the main information highway.
A conveyor belt. I like that.
Information can flow along this cell state with only some minor linear interactions.
Hmm.
It makes it really easy for information to just persist, to keep flowing unchanged down the chain for potentially a long time.
So it's designed for easy information preservation,
Hmm.
but how does it control what stays on the belt and what gets taken off or added? It can't just keep everything forever, right?
Ah, good question. That's where the gates come in.
Gates, okay.
These are the structures that regulate the information flow into and out of the cell state. They can selectively let information through or block it or add new stuff.
So they're like gatekeepers for the memory conveyor belt.
Exactly. And the way they work is quite clever. Each gate typically consists of a sigmoid neural network layer.
The one that outputs values between 0 and 1.
Precisely. Think of it like a dimmer switch. 0 means let nothing through, 1 means let everything through, and values in between mean let some proportion through.
Okay.
And that sigmoid output is combined with a pointwise multiplication operation. So it multiplies the incoming information by the gate's 0 to 1 output, effectively scaling it down or letting it pass unchanged.
So the gate learns, based on the current input and past context, how much of some piece of information should pass.
You got it. And a typical LSTM has 3 of these main gates controlling the cell state.
3 gates managing that central memory. Okay, let's break them down. What's the first one?
The first step is deciding what information we're going to throw away from the cell state.
Yeah.
This decision is made by the forget gate layer.
The forget gate. Makes sense. You need to clear out old stuff sometime.
Exactly. It's a sigmoid layer, like we discussed. It looks at the previous hidden state. That's kind of like the output from the last time step, the short-term memory, and the current input data. And based on those, it outputs a number between 0 and 1 for each number in the previous cell state, CT1. 1 means definitely keep this piece of info. 0 means definitely get rid of it.
So it decides, piece by piece, what's no longer relevant from the long-term memory.
Right. Think back to our language example. If the cell state is holding the gender of the subject Mary, and then the next sentence starts talking about Bob, the forget gate might output values close to 0 for the Mary gender information, effectively forgetting it to make room for Bob.
Okay, clearing the slate for new relevant info. Makes sense. So step 1, forget some old stuff. What's step 2?
Step 2 is deciding what new information we're going to store in the cell state. This actually has 2 parts.
All right.
First, there's the input gate layer, another sigmoid layer. It decides which values will update, like which parts of the cell state are going to get new info.
Okay, so it flags the spots for updates.
Yeah. And second, a TAN layer creates a vector of new candidate values. Let's call it C tilde T. These are the potential new pieces of information that could be added to the state.
TON, that squashes values between Monica's 1 and 1, right?
It does. So you have the input gate deciding what to update and the TON layer creating the potential new values.
So back to Bob, the input gate might say, okay, we need to update the gender information, and the TON layer creates the representation for male.
Exactly, that kind of process. It figures out what needs adding and prepares the new information.
Got it. So we've forgotten old stuff, we've prepared new stuff. How do we actually combine it all to update the cell state?
Right. This is the update step. It's pretty neat. You take the old cell state, CT1, and you multiply it pointwise by the output of the forget gate, FT.
Which zeroes out the things we wanted to forget.
Exactly. Then you take the output of the input gate and multiply that pointwise by the candidate values vector, C tilde T.
Okay, so that selects the relevant new information.
Right. And then you just add this result to the result from the forgetting step. So the new cell state CT is old state forget gate output plus input gate output candidate values.
Old stuff forgotten, new stuff added in the selected places. The conveyor belt gets updated.
That's the core update mechanism. You drop the old subject's gender and add the new ones.
Okay, that makes a lot of sense conceptually. So the cell state is now updated with the latest relevant long-term info. How does the LSTM actually produce an output for this time step? Like, what does it pass on?
Good question. The output, which is also the hidden state, HTT, for the next time step, is based on this newly updated cell state, but it's a filtered version.
Filtered how?
First, we run an output gate. Guess what? It's another sigmoid layer.
Huh, sensing a pattern here.
Yep. This sigmoid layer looks at the previous hidden state, HT1, and the current input, XT, and decides which parts of the current cell state C we're going to output.
Okay, so it selects what's relevant from the long-term memory for the current output.
Exactly. Then we take the cell state, CGA, push it through TAN.
To squash the values between -1 and 1 again.
Right. And finally, we multiply this TAN-squashed cell state by the output of our sigmoid output gate. Element-wise multiplication again.
So the output gate acts like a filter on the processed cell state.
Precisely. It lets through only the parts of the long-term memory that are deemed relevant for the immediate task or the next step. That result is HT, the hidden state for this step, which is both the output for this step and an input for the next LSTM module in the chain.
So maybe after seeing the new subject, Bob, the output gate decides the relevant thing to output now is that the subject is singular, because the next word might need to be a verb like is instead of are.
Perfect example.
Yeah.
It outputs what's needed for the next prediction or action based on its filtered view of the long-term memory.
Wow. Okay, that step-by-step really clarifies how those gates forget, input, output, and the cell state all work together. It's intricate, but it makes sense.
Yeah, once you break it down, the logic flows quite nicely. Forget, update, output.
Now, the source mentioned this is the sort of vanilla LSTM, the standard one, but there are variations.
Oh yes, lots of them. Research didn't stop with the original design. People have tweaked it in many ways.
Like what?
Well, one common variation adds people connections.
People.
Yeah. It basically means letting the gate layers, the forget, input, and output gates also get a look at the cell state itself, not just the previous hidden state and input.
Ah, so the gates can see the long-term memory they're controlling.
Exactly. Give them potentially more context for their decisions. It's not always used, or maybe only some gates get peepholes, but it's a known variant.
Interesting. What else?
Another idea is coupling the forget and input gates. Instead of deciding separately what to forget and what new information to add.
You make those decisions together.
Sort of.
Yeah.
Like you only decide to input new information in the places where you've just decided to forget the old information, or vice versa. Makes the update potentially a bit more focused.
That sounds potentially more efficient.
It can be. And then there's a really popular variant called the gated recurrent unit, or GRU.
GRU. Heard of that one. How's it different?
It's a more dramatic simplification. It combines the forget and input gates into a single update gate.
Okay, fewer gates.
And it also merges the cell state and the hidden state. So there's no separate cell state conveyor belt. It simplifies the whole module quite a bit.
Why do that?
The goal was fewer parameters, potentially faster training, easier implementation, while still hopefully capturing those important long-term dependencies. And GRUs have become really popular. They work very well on many tasks.
So simpler, maybe faster, often just as good.
Often, yeah. It's a strong contender. The source also mentioned others, like depth-gated RNNs, clockwork RNNs, lots of different takes on managing time and memory.
Seems like a really active area of research. Did the source say if any of these variants are definitively better?
Interestingly, some big comparison studies found that many of the popular variants, including the standard LSTM and GRU, perform remarkably similarly on many tasks. There wasn't always a clear winner.
Huh. So the original LSTM design holds up pretty well.
It really does. Although other research did find some specific, maybe more complex architectures that could outperform LSTMs on certain benchmarks, but LSTMs remain a very strong baseline.
Fascinating. So let's kind of wrap up the core LSTM part. What's the main takeaway from the source material on LSTMs themselves?
I think the biggest point is just how impactful LSTMs have been. That huge success we talked about earlier with RNNs, most of it is really thanks to LSTMs or variants like GRUs just working so much better than plain RNNs on most tasks.
They really correct that long-term memory problem.
They did. And the source mentioned that while the equations might look scary if you just see them written out, hopefully breaking it down step by step makes the underlying ideas, the cell state, the gates controlling, flow much more intuitive.
It definitely helped me. The source also hinted at what might be the next big thing, or at least a major development beyond LSTMs, something called attention.
Ah, yes.
Yeah.
Attention mechanisms. That's a really powerful concept that's often used with RNNs, including LSTMs.
So it works alongside them? How does it work?
The core idea is to allow the network, at each step, to selectively focus on different parts of the input sequence. Instead of just relying on the compressed hidden state, it can look back at the entire input and decide which parts are most relevant right now.
Like paying attention to specific words when summarizing a long document.
Exactly. Or in image captioning, when generating the word dog, The attention mechanism might make the network focus specifically on the pixels in the image that contain the dog.
So it adds another layer of dynamic focus.
It does. It gives the network a way to handle very long inputs more effectively by learning where to look. It's almost like giving the LSTM a spotlight to shine on the most critical information for the current task.
That sounds incredibly useful, a big step up again.
It has been. Attention is a key part of many state-of-the-art models now. And the source also briefly mentioned other cool directions, like grid LSTMs using RNNs for generating new data.
Like creating music or images.
Yeah, generative models. It just highlights that this whole field of recurrent networks is still super dynamic and exciting. Lots of innovation happening.
Okay, so summing up this whole deep dive, LSTMs were this massive leap forward, solving the long-term dependency issue for sequential data using that clever cell state and gate system.
Absolutely. They fundamentally changed what was possible.
And they're really the bedrock beneath so many of the smart technologies we use every day, even if we don't see them directly.
For sure. Speech, translation, text generation, LSTMs or their descendants are likely involved.
So thinking about all this, the power of LSTMs, the ongoing research, these attention mechanisms allowing even more focus, it really makes you wonder, doesn't it?
How so?
Well, given how fast things are moving, with these networks getting better at understanding context, memory, and now attention, what kinds of completely new applications, things we maybe can't even quite imagine yet, could be revolutionized by these technologies in the next few years? What future breakthroughs are waiting just around the corner?